right, well, we're just moving right along in our content, and upon discussing it, we think that we're somewhere in the midst of the Rhine Papyrus in our conversation. So I'm putting up this preface to the Rhine Papyrus. You'll actually find it in one of the PowerPoints that I posted in week 1. So this is one of the slides in there. So just so that we see it, the Rhine Papyrus, what we know is that it was actually a really ancient papyrus that was probably starting to crumble and fall apart. And in the year 33, this guy, Amos, was the scribe who copied it over. So this is just kind of the preface that he put at the beginning, just so that everybody knows, you know, this is a really old papyrus, and I am rewriting it, basically, trying to keep it alive and trying to make sure it doesn't go badly here. So I think that the dates on the Rhine Papyrus, we think the original was written sometime around 1700 BC, and they get that because of who the kings are, who the pharaohs are at the time. This was the original. This is the one that when it was rewritten. So because of that, they think that it was sometime around 1700 BC. But we know that the one that we currently have was copied in the year 33. So that's kind of interesting. Kind of makes it more modern and that kind of thing. More modern, you know. It's 33. That's 80, right? That's more modern than 1300 BC or 1700 BC. All right. So what do we know? I think we started talking about this just a little bit, but just to make sure, we're really certain that the Rhine Papyrus was used as a textbook of sorts. So probably it was used to say, hey, you're trying to learn your math, you need to know some problems, so here's some geometry for you, here's some fractions, here's some arithmetic. There were a lot of tables on it, and we'll talk today about one of the tables that was on it that was really important for our purposes and understanding how the Egyptians did stuff. And there were a lot of what they called exercises, and we'll talk about one or two of those today as well. So exercises being basically like word problems. So hey, go work on this kind of problem and see if you can do it or not. And what they would do is they would write out problem number 3 or whatever that we'll talk about today. The scribe would write it out, and then they would write the solution so that everybody could see how it was that they solved it and how the person learning was supposed to be able to do stuff. So kind of interesting. All right, so that's what we're working on. We talked about Arnold Chase having the most thorough translations. He had one book in 1927 where he did a strict translation, word for word, and then he had one book in 1929 where he did a free translation, and the free translation meaning that he was free to take some creative license and interpret things. So what this means is blah, 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 that kind of thing. So that's where we were when we left off last week, I believe. So, okay. Yep, I think that's where we were. So, what are we going to do today? We're going to do some work like they did in the papyrus. So, we're going to do multiplication first off. Multiplication like an Egyptian. It'll be so much fun. And for purposes of an exam, for purposes of a homework and things like that, you're going to need to be able to do this so that you can reproduce some stuff. So, you will see pop up into the D2L some homework assignments where I say, okay, use what you know about multiplication to do these problems. So same thing on a test. So for instance, what they did was they used a lot of doubling methods. That was their preferred means for multiplying. So instead of doing, say, you know, you have 22 times 5, instead of doing the 5 times the 2, write it down, do the 5 times the 2, move over, write those down in columns. They didn't have that kind of an algorithm like we do nowadays for multiplying. So they would do doubling because most people can double pretty easily. So for instance, say we want to do 26 times 13. Okay. For our purposes, we would, do the 2-column thing. 6 times 3 is 18, write that down, and so on and so forth. Move over 1, write down the 6, blah, blah, blah. So they're like, oh, this is our current modern algorithm. And I would say that if nothing else from this class, I hope that at some point you figure out that we have a lot of understanding in the modern day, and there's a lot of stuff that's kind of nice for us because we have modern notations and things like that. And just be grateful that you're living in the modern day instead of 3000 BC, because some of the stuff that they did takes a little bit more effort. So hopefully we learn to be grateful. Okay, so what I tell people is this is going to turn into kind of a math education problem. So instead of saying 26 times 13, they'll say like 26 groups of 13. You can read this one way or the other. 26 groups of 13 or 13 groups of 26. And in a math education classroom, this would be normally the first number would be the one that tells me how many groups. So that would be, you'd flip it, but we know we can multiply in any order we want, so it doesn't matter. Okay, so the 13 groups of 26 is actually easier to do because it's a smaller number of groups, so I'm going to show you that one. But if you want to do 26 groups of 13, you can do it that way and you'll still get to the same answer. It just takes a little bit longer to do the multiplication. So by doubling, what they would do is they would say, one group of 26 is 26. Okay. 2 groups of 26 is 52. Okay, so they just double it. They won't do the 3 groups because we're going to double, so we'll go straight to 4 groups of 26. And we double that, that's 104. And be careful here because a lot of times in homework and on tests, I'll see people do 6 groups, but that's not a double, right? So 4 times 2 is 8 groups of 26. And again, I'll double this number, so that's 208. And then I double the 8, I get 16 groups of 26, and that would be 416. However, whenever I look at my problem, I go back and I say, hey, I was trying to do 13 groups of 26. So do I need the 16 groups of 26? No, because it's too big, right? Okay, so I didn't need to go that big. So if you don't go that big, that's okay. You don't need it. Okay, but then I work backwards, so to speak. So I say, okay, I'm looking for 13 groups. So I've got 8 here. And I've got 4 there. 8 and 4 is 12 groups. I don't need the 2 because that would make me 14. I'm only after 13 groups. So I need 1. So if I add all those together, that gives me 13 groups. Okay, 8 plus 4 plus 1, 13 groups. All right, so then I go to the other side, and what I'm saying is if I want 18 groups of 26, then I'll add the 8 groups, however much that was, the 4 groups, and the 1 group, however much those are. So what I'm really after is 208 plus 104 plus 26, okay, which is not a bad math problem. It's all addition. So the thing about the Egyptians is they're probably going to mostly do additive stuff, just like their number system was additive, and they're probably going to mostly do multiplication. So what is that? 18, 338. Check my arithmetic always. Okay, so when we add that all up, 338. Now, in modern day, hey, we'll just punch that in the calculator, right? So that makes us really, really grateful for our modern calculators. 13 times 26 done. But it's kind of cool to see how they manufactured this. And we're going to talk about why it works here in a minute. So really pretty cool. All right, let's do another one. Yay, and I'm going to give y'all a second to work on one by yourselves. So let's do 18 times 29. Work on it for just a second, see if we can figure it out. We need 18 groups of 29. Okay, so I think one group of 18 is 18. Oh, what am I doing? I'm so sorry, you guys. I could do it that way if I wanted to do 29 groups, but I don't want to do 29 groups, so sorry about that. One group of 29s is 29s. Two groups of 29s, oh goodness, 58. Four groups of 29s is 16, 116? Is that right? Okay, check me. 8 groups of 29s, double that would be 32, 232. And 16 groups of 29s is 464. Hope my math is right. Always check my arithmetic. All right, and because I'm looking for 18 groups now, what do you think? I need definitely need the 16 this time, right? Because 18 is bigger than that. And then I need a 2, right? Because that'll give me 18 on this side. 18 groups. Okay. And then on this side, all I've got to do is add 464 plus 58. That's not terrible. I can mostly do that in my head. 522. Okay, so 18 times 29 better be 522. Okay, so it's really kind of cool, just a little doubling process. Mostly we can do that in our heads. If not, we can just use a nice scientific calculator to do some multiplication. And then some addition, which again can mostly be done in our heads. So not terrible. That's how they worked it. So the question pops up, well, why is it possible to do this? Why are they able to just double, double, double and it works out? And the answer is actually really interesting. It boils down to the fact that we're in a base 10 system, because we are in a base 10 number system. So, and theirs was a base 10 number system also, which is interesting. 10 fingers, 10 toes. So base 10 number system. And whenever we look at that, we say, okay, well, what are our place values in base 10s? 1, 10, 100, 1,000, and so forth, 10,000. Okay, and whenever I break down any number, doesn't matter where it is. So say I have, I don't know, I'm trying to get up to the number 41. Okay. Whenever I look at that, it's really 4 groups of 10s, so 40, and 1 group of 1. So there's that leftover guy, right? But the trick is right here in the place value. So the fact that I'm doing 4 groups of 10s, or if there was say a 7 out here, 7 groups of 100, it doesn't really matter what's going on in the placeholder here in either of these. What really matters is the place value. And because they're in base 10, when I look at those, I can break these down. I can factor them. That's a 2 times a 5. And this is a 10 times a 10, which is a 2 times a 5 and a 2 times a 5, right? And same thing for 1,000. That's 100 times 10, which is 10 times 10, which is 2 times 2 times 2 times 5 times 5 times 5. So interestingly, what we see here is this guy is 2 to the first times 5 to the first, right? And then that is times a 4. But we don't really care about that. What we care about is that the 2 goes into it evenly, okay? And same kind of things going on over here. This is 2 squared times 5 squared. Look, 2 squared goes into that evenly, right? It doesn't matter if this is an even number, an odd number, what that placeholder is. What matters is that the place value is evenly divisible by powers of 2. Okay, this guy's evenly divisible. You can, yeah, I mean, we know they're all base 10, they're all 2 times 5, and however many times I do that, right? Okay, so the weirdo for us is this guy right here. Okay, and what we know about him is he's actually, and I'm going to write him a little bit weird, he's 2 to the 0 times 5 to the 0, which is just 1 times 1, which is just 1, right? Okay, so, and I write him like that because I want to show, look, these are the powers of 2, right? When we did this doubling effect, 1 times 2, so this is 2 to the 0, this is 2 to the first, this is 2 to the second, 2 to the third, and so on, right? So every time we double, we're just multiplying by 2 again and again and again. So it's just times 2 times 2 times 2. That's what's going on. And that's actually what's going on in our place values, right? This is 2 to the third times 5 to the third. So I see 2 to the 0, 2 to the first, 2 to the second, 2 to the third, blah, blah, blah. So we know all of these are divisible by some power of 2. The weirdo is the ones position. Okay, but if we just think, oh, those are all the random leftovers, basically, those are the ones that are left over, then what happens is every number that we can think of, every positive whole number, okay, all of our positive whole numbers, positive integers, let's say, are comprised of some sum, let's say a sum of powers of 2, okay, because this is 700 plus 40 plus 1, right? It's the sum of some powers of 2. But inside of there, I know that's 7 times 2 squared times 5 squared, 4 times 2 times 5, and 1 times 2 to the 0, 5 to the 0, right? So it's some powers of 2. Now, we use the powers of 2, or the Egyptians use the powers of 2, but it's interesting to me they could have used powers of 5. Right? They just didn't, I don't know if they didn't see it or if it was too complicated to do the powers of 5, but it's really a lot easier to double than it is to multiply by 5, probably. So probably they were just working with kids or young mathematicians, so to speak. So they were like, hey, how can we do this? Or maybe they just kind of stumbled upon it and they didn't really realize that it is these sums of powers of 2, where the leftovers, the remainders, we can just treat those. I've got a 1 sitting there, but if I had a 3 sitting there in that place value, that would just be a 1 plus a 1 plus a 1. So it's still a sum of some power of 2s. So it's kind of interesting. That's why it's working out for us, which is cool. They could have used 5s, though. Boy, that would have made our life more difficult. Okay, so inside of the Rhind Papyrus, I hope that makes sense, how that works out with the powers of 2s. And why the doubling things works. But inside the Rhind Papyrus, they go from multiplying to division. So let's talk about division of whole numbers. And in general, they're using positive integers when they're doing things. So when we say whole numbers, they probably mean natural numbers is probably what they're working with the most. Okay, so division. In modern day math education, we would call division the opposite operation from multiplication, or sometimes people call it repeated subtraction, stuff like that. But we're going to think, for our purposes, backwards multiplication. And the reason why we're going to think of it as backwards multiplication is because actually the Egyptians did the exact same process for multiplication for their division. They just worked with it a little bit differently. So here we go. Like, I'm going to do the problem 324 divided by 27. Okay. But we're going to do it by doubling. So we're going to still use their technique that they already had, which is going to be so much fun for us. So just as a backup for us real quickly, in modern days we would call the 324 here would be our dividend. So it would be the total that we would get at the end, and the 27 would be the divisor. So like if we did it like this, we would end up with an answer back here, and the answer is the quotient. But so here's what I'm saying. I've got 324 items sitting there, and I'm going to take out a group of 27. And in repeated subtraction, I'll take out a group of 27 and another group of 27, and I'll just keep on taking out 27s until I have either nothing left or something that's smaller than 27, and then I'll have a remainder, right? Now this one's going to go in evenly, but we'll do one in a second that doesn't, okay? So what I get as my quotient is going to be the number of groups. Okay, my answer is going to be the number of groups. So a minute ago what we did, let me go back and rephrase this. A minute ago we knew we wanted, for instance, 13 groups. So we just doubled until we got to a number that was big enough to have 13 groups. And then we added our total, okay? But here it's backwards. That's what I'm getting at. So I know my total here. I don't know the number of groups. So instead of working off of what I would consider the left-hand side, like we did a second ago, now I'm going to work off the right-hand side. So I'm going to have, and this is my total, so it's just going to kind of wait until I get big enough numbers to get to 324, basically. So what I'm working with is my group is a group that is the size of 27. So I'm going to do 1 times 27. This is one group of 27, that's 27. 2 groups of 27, well, that's going to be 54. I don't want 3, I want to double, so 4 groups of 27 is 108. Okay. I need to do 8 groups of 27, so I need to double it again. So see, the process, the actual forward process is the exact same as what I did a second ago. Just double, 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 no big deal. So that's going to be 216. And then I check for 16 because we had to use 16 the last time I did this problem. But if I double this number again, that's going to be 432. And that's bigger than the number that I need. I need the total to be 324. So I'm going to stop because I know I don't need that big of a number. So somewhere in here should be numbers that will add up either to 324 or really close to 324. So notice that I'm going to work on the right-hand side. So that's the backwards part. I'm looking at the total now. So 216 plus 108, I was nice about this first problem, is 324. So it is actually exactly what I needed it to do. So in this one, I'm working to add up the total. And what I'm going to do is I'm going to find the number of groups. So I'm working on the opposite side. So the number of groups is going to be what's on the left-hand side, which is pretty easy. 4 plus 8, 12, right? So I've got 12 groups of 27 is equal to 324. Oops, 324. There we go. So my answer is 12. Which went in nice and evenly, and this actually totaled up to be the number that I was after. If it hadn't have been, if for instance it had been 330 divided by 27, then I would have these two. I'd have a leftover 6, and then I'd have to deal with the fraction part, which we'll get to in a little bit. Okay, but for right now, I'm not going to worry about fractions just yet. So these go nice and pretty. So far, so good. Okay. So for practice purposes, I do have some problems. I'm not going to work on right now. So if you want to play with some of these and make sure you can do them, I would say everyone try some problems. 52 times 11, 18 times 29. Those are some multiplication problems. And then on the other end of things, you could try 480 divide by 3, that one's fun. 72 divided by 6 is just a long problem. 72 divided by 6 and 375 divided by 25. So that gives some opportunities to make sure that you can just do this on your own and do the process over and over. I think it's a pretty straightforward process, but I'm not going to take those up or anything. Just practice. Just see if it works for you or not, if it makes sense. If you're good with them, then great. There'll probably be some homework that pops up at some point that'll that'll let us do some of those. Okay, so that kind of gets us into the whole idea of multiplying and dividing, and I want to do one problem that's not going to come out so nice and evenly. So here we go. What if it was, what about, so everybody try this one, 43 divided by 8. So remember, we're still doubling, we're still doing that same process, and we want to get to the total of 43. It doesn't take me very long to get to a big enough number that I'm like, oh wait, I'm in trouble. So 1 times 8 is 8. Hopefully everybody's doing it on their own. If you need to pause the video so that you can do a little math, it's okay. Pause the video and come back to us. 2 times 8 is 16. 4 times 8 is 32. 8 times 8 is 64. My total is only 43. So I know I don't need that 8 times 8. So I'm going to mark him off. Or if you never wrote him down, it's okay. So what I see here is 4 times 8 is 32. And that's not quite 43. But if I add 16, that's 48. That's too big. So I can't add the 16. I can't use him. So you're too big. And again, I'm working on the right-hand side because this is a division problem. But I can add the 8, right? Because 32 plus 8, that'll give me 40. Okay? Which is not quite the number I'm after, but it's pretty close, right? So I know I'm going to have a remainder. I'm going to have some leftovers. I'm going to have to deal with that. And that'll lead us into talking about how the Egyptians dealt with fractions. So what I do here is I'm going to use these two groups. So I need 4 and I need 1. So it must be 5 groups, right? 5 groups of 8 is 40, which we know. We've got our multiplication tables down pat. It's not a problem. But that's how the Egyptians would have done it, especially if they were learning their math. So what we really have here is we have 5 with a remainder of 3, right? Because it's 43. Or if you're thinking 5 and 3/8, right? Because we were dividing by 8, so that would be the fractional part. But there's my answers, okay? So the question that we're going to try to define next is, how in the world did the Egyptians deal with 3/8? Okay, so first off, we've got that math problem where we're doing the multiplication and the doubling and the dividing and all that good stuff. And then we're going to say, what did they do with the 3/8? So that's where I'm headed next. So stretch. Let's think about Egyptian fractions. Whew. Egyptian fractions. It'll be fun, fun, fun. All right. Egyptian fractions. So some stuff about Egyptian fractions. I didn't mention the notation the other day, so I'm going to go ahead and get it in here now. In general, the Egyptian notation would have looked like, if they wanted 1/8, they would have put their symbol for the 8, which probably would have been like 8 sticks, right, or something like that. And then they would have put a dot on top. Okay, so what we're going to see is that the Egyptians really had a notation issue. And we're going to really appreciate our fraction notation once we're done with this, I think. So they put a dot on the top. And the fact that they're using dots to represent the numerator of any fraction, that's actually a really big notation limitation. So they're really going to have problems with that. So because of that, because they've got this silly dot thing, we think that's the reason why, in general, Egyptians wanted unit fractions. Now, I don't know, but they wanted to work with unit fractions. And just think about it like this. You know, if I have 1/8, that's pretty easy. But what if I have 5/8, right? So if I'm trying to do something with 5/8 and using the same kind of notation, you know, they've got the 8 on the bottom. Are they going to put 5 dots on the top? I mean, how are they going to do that? So it's going to look really weird. So they didn't do that. They didn't have that kind of a notation. They didn't want to mess with it. So we're pretty sure that the reason why they insisted on working with unit fractions is just because they had that dot system going on. Okay, so working with unit fractions, and they didn't want to repeat. They didn't want to repeat a unit fraction. So these are some of the things that we have to keep in mind when we start working with fractions like the Egyptians did. They don't want anything that doesn't have a 1 on the top, and they don't want to repeat any of them. So we got to watch out for that. So for instance, let me pull this 5/8 since I've got him sitting right there. 5/8, they wouldn't write it 5/8. They might do something like pull out 1/8 because they see the 1/8 sitting there. And that leaves me a 4/8. And I like 4/8 because why? Yeah, that's a half. So whenever I have even numbers in the denominator, it's kind of nice because a lot of times they'll reduce, so sometimes those are fun and easy to work with. But the odd numbers are more difficult, of course. So I might be able to do something like that where I just pull out 1 unit and then whatever's left over is kind of nice and works well for me. So that might work in this case. So for instance, for the 3/8 guy that we had up there, let's just go ahead and deal with him. So we had 5 and 3/8. That method would work really nicely for this. I'd pull out a 1/8. I have a 2/8 left over, but 2/8 is nice because it reduces to 1/4, right? Okay, so for the Egyptians' answer up here, let's go ahead and finish out that problem. They would write 5 plus 1/8 plus 1/4. And that would be their answer for that problem. Okay. But what we see is sometimes that's their answer, and sometimes you might get a different decomposition. This is called fraction decompositions here. So sometimes we might get a different way of writing this. And what it really depends on is it depends on your approach to the problem. So we'll see some stuff that goes, oh, well, if I did it this way, then I get that unit fraction, but if I do it this other way, I get this other. So in general, if I can pull out 1 unit and then the rest reduces, that's nice, but sometimes it just doesn't quite work that way for me. So let's look at one that's not going to work quite so nicely for me. How about 3/5? Notice that I didn't change the numerator, the 3 is still the 3, but I did change the denominator, and now instead of being even, it's odd. It's got this lovely 5 on the bottom. And if I just pull out a 1/5, then I'm in trouble because I still have 2/5, and that's still not a unit fraction. What I can't do is I cannot say 1/5 plus 1/5 plus 1/5. That's not going to work for me because it's repeating. Right? So I can't do that. Okay. So stinker, that's not going to work for me. But what I can do is, and I'll load this into D2L so everybody can see it. The Egyptians had this lovely, and this is one of the tables, I mentioned it a little earlier, one of the tables in the Rhind Papyrus that was decrypted or whatever, is the 2 over n table. So enter the 2 over n table. Here's a lovely version of it. It's 2 over all the odd numbers starting at 3 and working their way through to 101. I think in the text that I'm loading in D2L, they might skip the 3s, the multiples of 3s, and I'll show you why in a second. So they might not have 2 over 3 in the table. They might not have 2 over 9 in the table. They might not have 2 over 15 in the table. So I'll load this one as well just so that you can have an easy reference. On a test, I will give you this table. Of course, I don't want you to memorize all this. That would be nonsense. There's no reason in that. Okay, but you will need to be able to read it and use it and all that good stuff. So here's an example of when I would do that. I have 3/5. I don't want it to stay that way, but if I pulled out 1/5, I would have a 2/5 left over. This is a perfect opportunity for the Egyptians to use their 2/n table. So all I have to do is look at the 2/5, figure out what the table says for it. Well, the table says that 2/5 is 1/3 plus 1/15. Okay, so I'll make a substitution. This guy is going to go away. 1/3 plus 1/15. Okay, so I've got 1/5 plus 1/3 plus 1/15. I'll rewrite it just to make it pretty. Okay, so I've got that lovely thing right there. And the only thing I need to worry about is, are any of my denominators repeating? They're all 1s on the top. I've got a 5, a 3, and a 15. So no repeaters. So that would be a nice unit fraction decomposition for 3/5. It would work out using the 2/n table. Okay, so I had to pull one out and then I used the 2/n table. So in our lecture, probably not today, probably next class period, we'll actually see a couple of other methods, but for today we're just going to do things the way the Egyptians did. So it's interesting because some of the stuff spawned the need for people to say, hey, how else could we do that? What's another way we can look at that? Here's you. You're welcome. All right, so what we're going to see is, let's talk about that 3 guy. So we've got, let's just stick a few of them up here. We've got 2/3. That one is 1/2 plus 1/6. And we've got 2/9, and that one is 1/6 plus 1/18. And we've got 2/15, which is 1/10 plus 1/30. And let's do one more. Let's do 2/21, which is 1/14 plus 1/42. So it's really interesting to me because this rhyme papyrus that's like from 1700 BC, it was rewritten in 333 AD. Oh, bless me, excuse me. And then, sorry about that. I did try to get away from the microphone. And then it was translated in 1900s, has really spawned a lot of people looking at it and playing with it and trying to see patterns, especially the 2/n table. One of our retired faculty members here in the department, Dr. Dorsett, one of the PowerPoints has information on there where he came up with some patterns that are in the rhyme papyrus, which are just like, wow. So he's just spending time playing with that. So it's interesting. But this one is actually a really popular pattern that's in here. So what we see is all of these fractions, these are all 2/n fractions, right? They're all odd numbers on the bottom, 3, 9, 15, 21. And each of these is a multiple of 3. 3, 9, 15, 21. You notice that the ones that I've skipped are the evens, so like 6 isn't in there, 12 isn't in there, because 2/6 is going to reduce anyway to 1/3, so we don't need that one in there. But these odd guys are in there. Okay, so what is believed, because it is the same for all of these are called the 3K guys. Okay, so 2/3 times 1, where the K here equals a 1. Okay, 2/3 times 3, where the K there is a 3. Okay, so that's why they're called the 2/3K guys. This is 2/3 times 5, where the K there is a 5. And notice that these are my odd integers, right? Positive integers. 1, 3, 5. This one's a 7. 2/3 times 7. K equals 7. So interestingly enough, this pattern that we're about to see works for every 2/3K guy in the rhyme papyrus's 2/n table. So it is believed that they knew the pattern we're about to say, because they didn't go into all these weird decompositions like they did with some of the others. Some of these are really in depth. Like, look at the 2 over 101 guy. It's 1 over 101 plus 1 over 202 plus 1 over 303 plus 1 over 606. Those are 4 really in-depth fractions. And we can prove that they're equivalent because all we need to do is get a common denominator, right? So 606 should be my common denominator. Multiply them all out, add them, reduce it, and it'll end up being 2 over 101. So these are all very in-depth, but look at the one right before it, 2 over 99. It's 1 over 66 plus 1 over 198. So it's a 2, it only has 2 fractions, same with the 93 guy. So they only have 2 fractions, the 81 guy, and they're all following the same pattern. So let's see if we can come up with a pattern, and then we'll make sure. So thinking about this as, okay, all the numerators are going to be 1 over something plus 1 over something. We'll figure out what that is. It'll be awesome. All of these numerators are going to be 1 over something plus 1 over something. If we just take a second to analyze it and think about what's going on with the k there, and some of you might have already gotten ahead of me. That's okay. What's going on with the k here? If k is 1, what could we do to the denominator here using a k to get a 2? Well, I could either add a 1, k plus 1 would give me 2, or I could multiply by 2, k times 2 gives me 2, 1 times 2. And we can see what other stuff there is. You could do all kinds of subtraction and whatever, but probably the Egyptians are going to be either multiplying or adding because they're pretty straightforward. So let's look at the first guy here. I could not, in this case, add 1 because 3 plus 1 would be 4, not a 6. So, but I could still multiply by 2. 3 times 2 gives me 6, right? So maybe the first denominator is k times 2. Let's keep going. Here the k is 5, so 5 times 2. Yep, that works. And here the k is 7, so 7 times 2 gives me 14. Yep. So the first fraction is 1 over 2k. Okay. In this case, it's 1 over 2 times 1, 1 over 2 times 3, 2 times 5, 2 times 7. Okay, that gives me that number there. Okay, so what about the second fraction? Similar thing, right? I could, here with the first number, 2 over 3, k was 1. I could do 1 plus 5 gives me 6, or I could do 1 times 6. Okay, so let's look here. K is 3. 1 plus 5, or 3 plus 5 does not give me 18, so it's probably 6 times 3, right? Okay, here with 5, 6 times 5 gives me 30. Yep, that works. 42, 7 times, did I say 5? Yeah, 6 times 5, sorry. 42 is 6 times 7, so that works also. So here we've got 6k, or in this case it was 2 times 6. I'm sorry. I wrote it backwards. 6 times 1, 6 times 3, 6 times 5, that gives me 30, or 6k. 6k here gives me 6 times 7, which is the 42. Okay, so what they see is anytime you have 2 over 3k, you can decompose it into 1 over 2k plus 1 over 6k. And it's an interesting little formula. And if you wanted to, you could verify it like you would a trig identity. So you could just, do what I said a second ago. Work on the right-hand side, get a common denominator at 6k. This would be 3 over 6k. This would be 1 over 6k. So 4 over 6k, and then reduce that, and you get 2 over 3k. So it actually ends up that it's something that's very provable, very verifiable, like a trig identity would be. And so we can say, hey, that's always going to work, and it makes sense. And it looks like the Egyptians knew it, which is cool. They had Maybe they didn't have the 3K and the 2K, like they didn't have the notation like we do nowadays, but they knew the pattern. They saw the pattern. Because let's look at one. Let's do the one I mentioned a second ago. 2/81. Okay. Well, if I pull a 3 out of the denominator there, that's 3 times 27, right? Okay, gives me 81. So if I look at that, that better be 1/2 times 27 plus 1/6 times 27. Okay. So that's going to be 1/54 plus 1/, I'm cheating, 162. Okay, check that arithmetic if you don't trust me, 6 times 27. Okay, but that's what it says in the Rhyme Papyrus, right, in our 2/n table. So here was the 2/81, 1/54 plus 1/162. So we can see it in there, and it's a really cool little pattern. So I think that the textbook, Dr. Anderson's textbook, actually leaves all of your 2/3K guys out of it because he's like, yeah, you can figure it out. You can figure out all those 2/3K guys because it's an easy pattern, right? But so that's what you're going to see in your text as you're reading. But I'm going to load this guy up so that everybody can see it. It's got the 2/3K guys in there. Just be aware, this guy's out there, and it's kind of a cool little pattern. Kind of nifty, something we can play with. All right, so that's what the 2/n table looks like. Let's do one or two. Come back to that problem. So how about, I want everybody to just play with the 2/n table for a second, and then we'll make it worse in a second. But first, I just want you to use 2/overs. So everybody do 2/75. Okay. 2/75. That's actually a 3K guy on the bottom. So see if you can break it down a little bit. Push pause if you need a chance to look at your math. 2/3 times 25 is what I have. So I think that that's going to be 1/2 times 25 plus 1/6 times 25, which should be 1/50. 1/, that looks to me like 4 of them would be 100, 150. Okay, so in my table, sure enough, 1/50 plus 1/150. So that one's pretty easy because he's the 2/3K guy. So what if it's not a nice, easy 2/3K guy? So how about 2/, let's get a fun one, 2/67. And right off the bat, these are pretty easy. You're just using the table. That's not bad. Okay, so the table's pretty easy. We just pull it up. 2/67. That one is ugly. This is why I don't make you memorize. At least not this stuff. 1/40 plus 1/335 plus 1/536. So it's literally a matter of just using the table that's sitting there. Okay, so that one's pretty easy. They're not always going to be pretty easy like that. So let's find one that's not so easy like that. How about I have right here 4/7. And I want you to so find a unit fraction decomposition, that's your directions, using the 2/n table. Okay, and like I said earlier, there's more than one way for us to do this, for sure. There's going to be 2 more techniques that we show that are more modern techniques that people have been inspired by the Rhine Papyrus to try to come up with ways to decompose unit fractions, or fractions into unit fractions, I should say. But before we get to that, we're just going to use the 2/n table. So I'm looking at it and I'm like, oh man, 4/7, that's not very nice. I don't really see a way for me to pull something easy out of it. For instance, I can't pull out 1/7 because that gives me a 3/7, and that doesn't help me any with the 2/n table, right? And it's not going to reduce. Like if it was sixths here, then 3/6 would be nice, but 3/7 isn't going to help me any. So there's lots of techniques. One of the techniques that I like to play with is, what if we pull out a multiple of 2 out of this one? So there's, and you just have to do these things and play with the fractions until you feel comfortable with them. So what if I said 2 times 2/7? Because it's a 4/7, right? And 2/7 will be in my 2/n table. So then I'll just have to multiply everything by 2 and hope that something works out for me. Maybe it does, maybe it doesn't. You just have to play with the technique and see, right? So what I know is I can't do 1/7 plus 1/7 plus 1/7 plus 1/7. That's not going to work for me. So, poo. All right. So what about this guy? 2 times 2/7. If I did that, it's 2 times, and 2/7 is 1/4 plus 1/28. I find that straight out of my Rhine Papyrus 2/n table, so I just plug it in. Okay, so the kind of cool part about that is now I just need to multiply through, right? So I get 2/4 plus 2/28, okay? And 2/4 is nice for me because that'll reduce to 1/2. And 2/28 is nice for me because that'll reduce to 1/14. Okay, so for this particular guy, 4/7, it's kind of a nice way of thinking about, oh, why don't I just kind of pull it down by a factor of 2, basically, reduce it down by a factor of 2, and then hopefully, especially if I know the guy in the 2/n table has an even number on the bottom, it'll reduce out for me, so that makes life nice. If there were odd numbers at the bottom, that kind of wouldn't help me much, but these are even, so that's nice. Sometimes I've seen people get stuck in a loop on these. So I'm just kind of warning you against that. For instance, I've seen people do stuff like 2/7 plus 2/7. Okay, because that's the same as 4/7. That's okay. And then they'll start reducing. Like I said, you can't do 1/7 plus 1/7 plus 1/7 plus 1/7. But I might be able to do 1/4 plus 1/28 for one of the 2/7, and then 1/4 plus 1/28. That's essentially what I just did up there, right? Because I just did 2 of them. So then you'd group them together. So you could maybe, I've seen people do like that before. I've seen people kind of get stuck with stuff like this, 1/7 plus 1/7 plus 2/7. And so they'll say, well, that's 1/7 plus 1/7 plus 1/4 plus 1/28. And then they'll try to do other stuff. So sometimes it just kicks me back to, this is still 2/7, right? So this one's not too bad because, again, I can do it like I did up above. But sometimes, like if you find yourself really circling around, like you just keep on going around the same mountain every time, and I just keep on coming back, and no matter what I do, I end up with 2 of those guys, so I don't end up with a unit fraction, then maybe step back for a second and try a different method, okay? Sometimes instead of factoring out a 2, like I did here, people might try to multiply by a 2, okay, to make things more even. So instead of 4/7, you might say, let's try 8/14, okay? Now we know 8/14 reduces back down to 4/7. Oop, that was 4/7. Okay, so 8/14 is going to reduce back down to 4/7, but maybe it's like, oh, I can play with this because, look, that's 1/14 plus 7/14, right? Which gets me back to this original guy that I had up here with the half guy. 1/14 plus a half. But maybe people can see when they look at that denominator as even, they can see it easier. Oh, that reduces, okay? So some people will say, oh, let's just multiply everything by a 3. Okay, try it and see. So some of them you just got to play with it a little bit and see if the technique works for you. I will say on a test, whenever I say you must use the 2/n table, for my purposes, you have to use it once in that problem. So if you get into it and you're like, okay, I use the 2/n table, but I still see this problem, and you're like, oh, I wish I could do the splitting identity, which we'll learn next time, then you can. So I'm okay with you switching techniques as long as you've done the technique I asked you to do at least once. So just be aware that that's going to be out there. Okay. All right. So sometimes they'll do some division problems and they'll end up with stuff that is not dividing evenly. So 37 divided by 7, for instance. We had that problem earlier where we had the leftover 3. It was 43 divided by 8, I think it was. So if that's the case, then just realize that for the Egyptians, they're going to have to do 2 different pieces of math. First, they're going to have to do the division problem, which is using the doubling method, okay, to get them to how many total groups. And then they'll have the remainder, and then they'll have to do something with those fractions, decomposition-wise, to deal with those fractions. So just realize there's extra stuff in there you have to play with. So there we go on that one. What did I just say? Oh, I know what I wanted to say. Okay, so one more thing before we're out of time here. In the Rhind Papyrus, problem number 3, I mentioned it earlier, says something like this. And I actually think it's cool because it ends up being, people go, oh, that's kind of modern mathy. But it's really not modern mathy. It's actually really ancient mathy. We just have gotten away from some of the roots. So this is what the problem says. They want to split 6 loaves of bread among 10 men. Okay, that's what they tell you to do. So for our purposes, modern day, again, please appreciate our modern technology, our modern notations. We would say take 6 divided by 10, right? 6/10, that's 3/5. And we would take a loaf of bread, for instance. Here's a loaf of bread. We divide it into 5 somewhat equal pieces. We'll call them equal. And each person would get 3 pieces, right? You get 3 pieces and you get 3 pieces. And it'll all work out. So you would get 3/5 of a loaf of bread. Because we know it's not 1 loaf because there are 10 men and only 6 loaves, right? So we don't have enough for everybody to get a full solid loaf of bread. So that's the way we do it modern day, and it works. It's fine. But I think it's interesting to look at it the way that apparently the scribe on the Rhind Papyrus had them work this problem. So they actually went back and said, hey, you got 6 loaves of bread. So kind of it's going to look like this. Here's your 6 loaves of bread. Again, we know it's not enough for everybody to get 1, but let me stop at 5 loaves of bread. If I only had 5 loaves of bread, that would actually be an easier problem to split amongst 10 people. Because what we would do is what? Yeah, just cut it in half. So 5 loaves of bread is actually pretty easy, right? It would be like, boom, boom, let's cut them all in half. This is a very modern math education problem, by the way. Okay, split everything into halves. Who would have thought they were doing this like 2000 BC? Okay, you get a half of a loaf of bread, and you get a half. It's like an Oprah moment. You get a half of a loaf of bread. So everybody gets a half of a loaf of bread. That's pretty easy to see for the 5 loaves of bread, right? So we see 6/10. That's 3/5. But they would have basically, the idea here, and we'll use this idea next week, the idea here is pull the largest unit fraction out you can possibly pull. So 1/2 is actually the largest unit fraction possible. So everybody gets a half a loaf of bread. So that's 5 loaves. But the problem is they wanted 6 loaves, right? And we know 3/5 isn't 1/2. I'm not done with my problem yet. Don't think I'm crazy. Okay, so I'm not done yet. So the problem is the 6th stinking loaf of bread. But what the Egyptians would then kind of say is, okay, but now you just have 1 loaf left, and you need to split it up among 10 people. So that's actually pretty easy also, right? I'll take that 1 loaf of bread. I need one more. And I'll split it into 10 pieces, and then each of these is 1/10 of that loaf of bread, and 1/10 of a loaf of bread, and 1/10 of a loaf of bread. And that's pretty easy because each of these